Hello students, good afternoon. We are discussing today BSc semester 5th unit 1, that is vector spaces in mathematics. Okay. Now let us tell you the definition of the vector space first of all. Let f comma plus comma dot means it is addition and it is multiplication be a field. This is the field which is explained in bracket here, f comma plus comma dot be a field. The elements of f will be called scalars, means those elements which we take from f, those are called scalars. Let V be a non-empty set, and V is any non-empty set we have considered, whose elements will be called vectors. The elements which present in V are called vectors and the elements which present in F are called scalars. Then if the following, then an ordered triple which one? This is V comma plus F comma plus comma dot means this is vector, okay, which is non-empty sets considering vector elements with plus, and this is field which is considered as the elements of field f is considered as the scalars with plus comma dot and single dot is there. Then this is called triple, 1, 2 and 3. That's why it is called triple. Ordered triple is a vector space. This ordered triple is a vector space over the field f. This ordered triple is a vector space over the field f if the following conditions are satisfied. Which conditions? Let us see those conditions which it must satisfy to be a vector space over the field f. So first point in this vector space condition is there is defined an internal composition in V called addition of vectors. Internal composition in V called addition of vectors and denoted by plus. Addition of vectors are denoted by plus here. Also in bracket V comma plus is an abelian group. Means this must be an abelian group such that closure property, in closure property V is closed with respect to addition. Means if we take two elements from V, which is, see here, V be a non-empty set whose elements will be a vectors. Means these vectors we have considered alpha is element of V and beta is element of V. It implies that alpha plus beta is also element of V for all alpha beta is element of V. This particular property is known as closure property. This particular property is known as closure property. Means we can say that V is closed with respect to addition. Means alpha plus beta, if alpha and beta both are element of V, then it implies that alpha plus beta should also be element of V. This is the closure property. Now commutativity, addition is commutative in V. Commutative property you know very well, that is alpha plus beta is equal to beta plus alpha. Here alpha plus beta should be equal to beta plus alpha for all alpha beta is element of V. Means this is only the non-empty set. V is the non-empty set whose elements are called vectors. So for all alpha beta is element of V. Now see third property, it is associativity. Associativity means addition is associative in V. Associative also you know very well that alpha plus in bracket beta plus gamma is equal to alpha plus beta in one bracket then plus gamma. If this one is equal to this one, then we can say for all alpha beta gamma is element of V. Means vector space V. Then we can say that addition is associative in V. If these are not equal, then associativity not true. If they are equal, alpha plus in bracket beta plus gamma is equal to alpha plus beta in one bracket and then plus gamma. For For all alpha, beta, gamma is element of V. Now, existence of identity, you know very well. There exists a unique vector 0. You know very well that if we add 0 in any element, then that element will remain same. Okay, that's why there exists for addition. For addition, we can say existence of identity is 0 only. So there exists a unique vector 0 vector called 0 vector or origin in V. This 0 vector is also known as origin in V, such that alpha plus 0 vector is equal to alpha is equal to 0 vector plus alpha for all alpha is element of V. Here again the same thing, it is this V is a non-empty set whose elements will be called vectors only. So here this existence of identity we have explained. Now existence of inverse. Existence of inverse, that is that you know very well, if 2 is any element and what we have to add in it by which we can get identity of addition. Suppose 2 is there, then we have to add minus 2 in it for getting identity, because 0 is identity only. So for alpha, if we consider alpha is element of V, means which is vector only. See, non-empty set having vector means this. In this alpha, if we are adding minus alpha, means a unique vector, there exists a unique vector minus alpha is element of V. For alpha is element of V, for every vector alpha is element of V, there exists a unique vector minus alpha is element of V, such that if we add alpha with minus alpha, then we will get the 0 vector here, or if we add minus alpha with alpha, then also we will get the 0 vector. In both the conditions, we will get 0 vector here. So this is only the first point, which is defined as an internal composition. Means it is well clear from here that internal composition is totally related to the operation, mathematical operation plus. This internal composition is totally related to the mathematical operation plus, we can say, where we have given all these properties, 5 properties, which should be satisfied for V plus to be an abelian group. So after this we will discuss second point now. Now see, it is second point. There is defined an external composition in V over field F called scalar multiplication, denoted by dot. Again, see, there is defined an external composition in V over F or field F called scalar multiplication, denoted by this dot, connecting the group and field. This is group and this one is field. Group and field, that is, if A is element of F and alpha is element of V, it implies that A alpha is element of V. This is only called the external composition. In internal composition we have discussed related to plus operation, plus mathematical operation, but in external composition this dot operation we have to discuss. So if A is element of F, means A is element of field and alpha is element of this V, which is non-empty set having vectors in it. Okay, so if A is element of F and alpha is element of V, it implies that A alpha is element of V. For all, A is element of F and alpha is element of V. You remember one thing, this should be denoted here also afterwards. Now, third point, these 2 points are well clear, internal composition and external composition. Now, third point, the 2 compositions, that is scalar multiplication and addition of vector, satisfy the following postulates. Scalar multiplication and addition of vector. Scalar multiplication and addition of vector satisfy the following postulates. These 2 compositions. See, here A, which is scalar, in bracket alpha plus beta, which are vectors. So it will be A alpha plus A beta. A alpha plus A beta. For all, A is element of F and alpha beta is element of V. Now, if we are taking 2 scalars here in bracket, that is A plus B with plus operation, and then alpha is with dot operation, then it will be A alpha plus B alpha. For all AB is element of F, means these are scalars, and alpha is element of B, means alpha is vector. Now third point, AB into AB bracket dot alpha can be mentioned as A and in bracket B alpha. For all AB is element of F, means these are scalars, and alpha is vector, means alpha is element of V. Fourth point, that is 1 into alpha is equal to alpha. For all alpha is element of V, means it is vector, and 1 is unity element of field F. 1 is what? It is unity element of field F. We have discussed one existence of identity there in addition, that was 0. Here in multiplication we know very well that if we multiply 1 with any vector, then there will be no change in that vector. This is called unity element of field F here. So this notation is cumbersome. It is tough to write in this manner. V plus, then F, comma plus, comma dot, and then comma dot, which is triple, and which we have discussed here totally. We can assign vector space over the field in this manner also. V and then in bracket F. Vector space over the field F can be represented by this notation also. We can denote it by this also, V and in bracket F. So this particular definition of vector space is now over, and I have explained you internal and external composition both. So we are just closing this topic here only.